Learning outcomes. Dear students, after studying this module, you shall be able to know about the significance of column chromatography, the principle and methodology of column chromatography, and the general aspects of column chromatography. Now, let us start with the introduction of this module. Chromatography, as you all know, is a technique used for the separation and analysis of complex mixtures. The separation phenomena was first reported by a Russian botanist, Michael Sweat, in 1906. He separated different colored constituents of plant extract by passing them through a column of finely divided calcium carbonate, alumina and sucrose. Sweat observed that various pigments such as xanthophylls and chlorophylls appeared as colored bands on the column, and he coined the term the chromatography for this technique. Greek word chroma means column and graphene means to write. Many advances have been made in this field in the last century, notably by Martin and Singe, who introduced the concept of gas-liquid chromatography in 1941. They were awarded Nobel Prize for their contribution to chromatographic science. Broadly, chromatographic techniques can be divided into planar and column chromatography. As the name suggests, planar technique incorporates the use of a flat, planar, two-dimensional surface where only length and breadth are taken as area on which chromatograms are formed. The surface is coated with the stationary phase. Paper chromatography, thin layer chromatography or TLC, and high performance thin layer chromatography or HPTLC are different types of planar techniques. Column chromatography has a stationary phase held in a column or a narrow tube. Most common types are gas chromatography or GC and high performance liquid chromatography or HPLC. Next is principle of centrifugation. Column chromatography separations involve stationary phase being held in a narrow tube or column. The mobile phase or eluent along with a mixture of component or solutes is forced through the tube having a stationary phase under pressure. This process is termed as elution. Eluate is fluid emerging from the end of the column. Columns are either packed or open tubular. Packed column is filled with small particles of stationary phase, whereas open tubular column is usually a narrow capillary tube with stationary phase coated on the inside wall. Next, we will be studying about classification of column chromatography. Chromatography is a dynamic process and all its types involve two immiscible phases. One is stationary phase, which stays inside the column or on a planar surface, and the other mobile phase, which moves through the column or over planar surface. Mobile phase can be liquid or gas and helps in redistributing the components of a mixture between two phases, thus aiding in separation. The stationary phase can be solid, liquid or liquid adsorbed on solid or organic species bonded to solid surface. Solid forms include non-exchange resins. The table here next classifies the various types of chromatographic techniques based on the type of mobile phase used, liquid, gas or supercritical fluid. Supercritical fluid mobile phase method is relatively new and is gaining popularity. Liquid chromatography can further be divided into 5 categories depending upon the stationary phase used and the mechanism of redistribution followed to attain equilibrium. Components of the mixture follow different mechanisms of interaction or redistribution, namely adsorption, partition, ion exchange or size exclusion. Likewise, gas chromatography can be further subdivided into 3 types. It is to be noted that liquid chromatography can be carried out in column as well as on planar surface, but gas chromatography and supercritical chromatography can only be performed in a column. In supercritical fluid chromatography, wherein the mobile phase is a superficial fluid, there occurs a partitioning between supercritical fluid and the bonded surface. Next, we will be studying about the process of elution. The process of elution and separation of various components by column chromatography has been depicted in this diagram. A solution having component A and B in the mobile phase is introduced at the head of column. Elution process begins when addition of fresh solvent or mobile phase or eluent which is applied onto the top of the column. The mixture of A and B is washed down into the column and these components distribute themselves between mobile phase and the stationary phase. The average time spent by a particular component in either stationary or mobile phase depends upon its affinity for that phase. In this diagram, the component B is retained on the stationary phase for longer period than component A. These difference in their rates of movement, that is A moving faster than B along the length of the column, causes the components of the mixture to separate into bands or zones. Complete isolation of the separated components is achieved by passing sufficient mobile phase through the column and collecting or detecting them at different times, having times of T3 and T4. Next, we will study about the chromatogram. Various solutes emerging from the column are observed with detectors. The detectors may be specific for the type of solute detected and are described in later modules. A chromatogram is a graph showing the detector response plotted against a elution time. Such a plot is useful for carrying out both qualitative and quantitative analysis. The positions of the peaks on the time axis are used for qualitative analysis, whereas the peak areas reveal the quantitative aspect of the components. Before proceeding ahead, we should be aware of certain terms used in column chromatography, and that is why the very first term that we will be taking up here is retention time. Retention time is a time taken by a solute to reach the detector after the mixture is injected onto the column. It is represented by TR. Adjusted retention time, that is TR dash, is given by the expression TR dash is equal to TR minus of TM, where TM is the time taken by unretained species or mobile phase to reach the detector. It is also referred to as dead time. So, the adjusted retention time for a solute is to move through the column beyond the time required by mobile phase to travel through the length of the column. The very next term in this is the partition coefficient. The solute components partition themselves in the mobile phase and stationary phase as they move through the column. If the column is run slow enough, the concentration of solute in the stationary phase and mobile phase reaches equilibrium. The equilibrium constant or partition coefficient K for this reaction is defined as K is equal to Cs divided by Cm, where Cs is the molar concentration of the solute in the stationary phase and Cm is the molar concentration in the mobile phase. Most of the chromatographic separations are performed under linear conditions, that is Cs is directly proportional to Cm. Thus, for solute X, it may be written as. Next term is the capacity factor. It is also called retention factor and is used to describe the rate of migration of solute on column. The capacity factor K dash is defined as K dash is equal to Tr minus Tm whole divided by Tm. This equation implies that longer a solute is retained by the column, greater is the capacity factor. If this factor is in the range of 20 to 30, elution time becomes too long. But if it is less than 1, then solute passes out without interacting with stationary phase. Ideal values lies between 1 to 5. Next term is the selectivity factor or relative relation, and it is denoted by alpha. This term describes the extent of separation between two components. Greater the value of selectivity factor or relative retention alpha, greater is the separation between closely spaced components in the chromatogram. It is expressed as alpha is equal to Kb dash divided by Ka dash, where Kb dash is the capacity factor for more strongly retained solute B and Ka dash is the capacity factor for solute A, which is eluted faster. It can be rearranged to give alpha is equal to TRB minus Tm divided by TRA minus of Tm. Both capacity factor and selectivity factor can be easily calculated from the chromatogram and are used to monitor the performance of column. Next, we will study about measures of column efficiency. Column efficiency depends upon how well the column is able to separate the components of the sample. Two factors contribute to this aspect: width of peak and difference in retention time between peaks. Wide peaks result in poor separation, and peaks having very close retention time may not be able to resolve completely. We will deal with peak width before elaborating upon resolution of the peaks. First is effect of peak width. The width of chromatographic peak as is recorded on chromatogram is the culmination of various phenomena taking place in the column. So, we will elaborate on theoretical terms related to rate of movement of a solute down a column. Efficiency of separation can be attributed to the concept of height equivalent to theoretical plates, or HETP, or simply plate height. A theoretical plate is an imaginary concept that does not conform to any actual parameter in the column, but for evaluation purposes it is a useful measure. Plate height refers to the length in the column within any two adjacent plates. The name is derived from the theory of distillation, in which column is made up of series of bubble cap tile plates and separation is performed in these discrete stages or plates. Plate height is the length that is able to achieve equilibrium of the solute between stationary phase and mobile phase under particular set of conditions, such as flow rate, temperature of column, type of stationary phase, etc. The solute then moves down the column with equilibrated mobile phase in a stepwise manner from one plate to the next. The concept of theoretical plate in chromatographic column was given by A. J. P. Martin and R. L. M. Cinch, for which they were awarded Nobel Prize in Chemistry in the year 1952. Here the figure shows separating column for separation of various components. The efficiency of the column to separate components is dependent upon plate height. A column of a particular length with lesser plate height and thus more number of theoretical plates is more efficient than the one with lesser number of theoretical plates. For a solute passing through a column of length L in centimeters having n number of plates and h plate height in centimeter, correlation between them is given by the expression where n is equal to L by h. Difference between plate heights of various solutes arises due to difference in their partition coefficients. Plate height can vary between 0.1 to 1 millimeter in gas chromatography and approximately 10 micrometer in high performance liquid chromatography. Plate numbers can range from a few hundred to several lakhs. W is the peak width or bandwidth. W1 by 2 is the bandwidth at half height of the peak. We can assess the efficiency of the column from the chromatogram by visualizing the shape of the peaks. A smaller plate height translates into symmetrical, narrow, Gaussian shaped chromatographic peaks, and reverse is true for peaks with greater peak width. To calculate n from chromatogram, the expression that is used is n is equal to 16 in brackets Tr divided by W whole square. Here Tr and W are time measurements in the same unit. Length of the column L should be known to obtain plate height of h. Another method for obtaining n, which some researchers prefer, is by using peak width at half height. Number of plates is then given by n is equal to 5.54 multiplied by Tr divided by W whole raised to the power 2. The results obtained in both cases are comparable. Since past 50 years, researchers have been devoted to developing meaningful relationships describing the effects of experimental parameters for reducing plate height on various columns. As the solute move through the length of the column, band broadening is observed, which is reflected as broad peaks on the chromatogram. This phenomena is inevitable. So, conditions have to be reached upon where it occurs slower than band suppression. Several physical and chemical factors decide the rate of band suppression and band broadening, and these are discussed in the chapters on gas chromatography and high performance liquid chromatography. Next is effect of retention time or resolution. The resolution is a measure of low well two adjacent peaks are separated by a column. Baseline separation should be achieved for complete resolution. This figure illustrates the performance of three columns with different resolving power for two components, that is A and B. The solution here is defined as R is equal to twice of delta Z divided by WA plus WB, where it is further equivalent to 2 multiplied by TRB minus TRA divided by WA plus WB, where the terms on the right side of the equation have been illustrated in this following figure. As it is clear from the figure, the resolution of 0.75 results in incomplete separation. At a resolution of 1, there is 4% overlap of peak. Complete resolution is obtained at values 1.5. The resolution for any given stationary phase can be improved by using a longer column. This increases the number of plates, although it also increases the time required for elution. A compromise is generally made between time taken and resolution. It has been observed that resolution is proportional to square root of n. Therefore, doubling the column length increase resolution by under root 2. It is, however, more effective to vary capacity factor k dash or selectivity factor alpha by varying the mobile phase for liquid chromatography and stationary phase for gas chromatography. Now, students, let us summarize this module. Chromatography is a separation technique involving mobile phase and stationary phase. Components of the mixture are separated on the basis of their affinity towards either of these phases. Column chromatography occurs in narrow column and depending whether mobile phase is a liquid or gas. It is called liquid chromatography or gas chromatography. These are further classified on the basis of nature of a stationary phase that has been used. A chromatogram is a graph showing the detector response plotted against elution time. The positions of the peaks on the time axis are used for qualitative analysis, whereas the peak areas reveal the quantitative aspect of the component. Partition coefficient, retention time, capacity factor, selectivity factor are the terms used to describe the affinity of the solute for a stationary phase or the residence time of the solute in the column. The efficiency of the column to separate components is dependent upon plate height, an imaginary but useful parameter. A column of a particular length with lesser plate height and thus more number of theoretical plates is more efficient than the one with lesser number of theoretical plates. The resolution is a measure of low well two adjacent peaks are separated by a column. The baseline separation should be achieved for complete resolution. Complete resolution is obtained at values 1.5.